Hello, everyone. I'm joined here by Mr. Navin Bishnoi, the Associate Vice President and India Country Manager at Marvell India Private Limited. Thank you so much, sir, joining us today.
Pleasure to be here. Look forward to the discussion.
Great, sir. So, to begin with, as per what I understand, Marvell has evolved significantly around data infrastructure in the past recent years. So, from your vantage point, what are the key technology shifts that are driving this evolution across the industry?
Uh, Good point and observation. If you look at what's happening is today we are all talking about the digital footprints across the ecosystem. Whatever you and I do from morning to late night, and even when we are sleeping, and in many use cases around us, it's significantly digital footprint, and semiconductor is the foundation of that footprint, right? I think that's an acknowledgement that started happening very recently, while this has been the case for many years, but now with the growth and the awareness, people acknowledge that semiconductor is the building block for it. Now, as we build those semiconductor technologies for this, you'll have to realize that there's a lot of these is built around the data, right? We are all generating data and we are consuming data through our gadgets, through our things that we do around. And there's a huge infrastructure that's needed to manage this data. And what is this data infrastructure? When we generate the data, it needs to be processed. It needs to be moved around. It needs to be stored. And then while doing all of this, it needs to be kept secured, right? So Marvel has been focused on creating these semiconductor solutions for data infrastructure. So we generate processors, networking elements, storage elements, and security elements across the use case, and specifically in the areas of cloud, AI, data center, enterprise, carrier, and many other particular functional domains. So those are the driving factors which has evolved Marvel into a data infrastructure, into an AI infrastructure company, and being the foundation of the digital footprint that we see around us.
That's great. And you have, personally been leading custom ASIC design across domains. So, what fundamental changes are you seeing in how silicon is being designed for modern workloads today?
Yes, so what has happened across when we go from a generation to generation, when internet came, mobile came, the whole cloud came, and now IoT, automotive, and AI, right? As we mature around these technologies, we figure it out what are the silicon components that exist, right? And they usually in our world we call it as a standard products or merchant silicons that you can foresee what the standards are, what the next generation requirements are, create and put it on the shelf and ensure that there is 5, 10, 100, or thousands of customers and use case can be leveraged using those CPUs, the general purpose GPUs, the memory elements, the networking, and all of that. But every time these transitions happen from a technology or disruption or something, an enabler for the next generation of what we call as a digital or the semiconductor footprint, that's the time what we also realize that there's always a need that come in about building a custom silicon and what we call as a purpose-built silicon. Think of it as that, like as we are starting the AI journey, the use case that you and I have, right? There is a training versus inference. There is hyperscaler versus enterprise. There is a use case of that your inputs could be text, audio, video, 3D, voice, and all of that. And the output could be again any of these and or a combination of these, right? The workloads are different. And as we are evolving, there's a set of footprint of what we call as a general purpose silicon elements that goes into these data centers and AI. And then there are purpose built that start coming in because of multiple reasons. And we can talk about it. And that's what is called as the custom silicon or a custom ASIC business, where you go and optimize it for a particular use case and get the best power performance and cost out of it and enable your use case. As we move forward, some of these will become merchant or general purpose, but there always is a balance of saying, what do you use as a general purpose versus what do you purposely build because you have a secret sauce, you have a secret recipe, or you have a cost mandate that you want to manage and build a complete solution to an end user in the world of AI, but this has been there, even the world of cloud, the networking, and many other disruptions that came earlier.
Mhm. And as you mentioned, AI infrastructure is increasingly constrained by the data movement rather than the compute. So, from the design
Yeah.
perspective, where do you see the biggest bottlenecks today?
Yeah, so just so that you understand before I get into that, right? I think, and for the audience as well, right? If you look at the difference in a traditional data center and an AI data center, right? One, we are talking about humongous scale of infrastructure, right? If you're training a model, we are talking about a million of XPUs, right? The processing units that needs to be there.
Mhm.
And then we are hearing about the power it consumes, the cost it takes, the size of the silicon itself, the cost of building that silicon, the number of size of models, the amount of data changes that's happening.
Mhm.
So AI infrastructure is at a peak of what we call as the complexity of multiple orders coming together and for us to optimize. But if we just break it up into three things, right? We need processing power, one for training, one for inference, which means we need hundreds and thousands and millions of these processing elements connected together. If we
Mhm.
break these processing elements, you have what we call as a general purpose GPU, which are good at what it was originally and could fit in into some of the use cases of the AI. But then there are also what we call as the custom XPUs that starts coming in because you're optimizing for a particular use case. And it's not just the XPU or GPU that comes in. There are a lot of other co-silicon elements that comes around us. You need a general processor to monitor and control some of the data movements. You need accelerators, you need co-processors for storage, for networking, for security, and all of that. So the compute infrastructure itself is multiple silicon elements rather than just one general purpose GPU or a custom XPU, right?
Mhm.
But now these are put, let's say, in a physical real estate space, and they need to be connected to each other and should work very fast because all of us, just like we are used to a search engine, and then we type and we get a response like instantaneously. How does our prompt also respond instantaneously? And hence, you need to ensure that the networking is fast. And
Mhm.
then they need to be connected. So there is millions of networking or connectivity elements that comes together to
Mhm.
ensure that they are connecting to each other. Now, it cannot be one-to-one mapping, and hence they are connected more as a network. So hence you need a switch to go from one network to another, one cluster to another, or a one physical space to another. And and then there's a lot of data that's getting generated during the processing as well as after the processing. You need to have space for, I think, local cache or a local storage as well as a long-term storage. So hence you have storage elements and all of that. So that's the three components that you have. Now,
Mhm.
when you are sending the data through your prompt to this cluster, when this cluster is distributing this problem into many compute element and hence going through the network, some of them needs to be locally stored, some of them need to be stored for a longer duration. Networking is becoming the bottleneck, and memories as well, but we'll come to that probably later. But networking is becoming the data is the bottleneck, and to the point, the fact or the I would say study says that if 50% of the time the data is moving rather than either at the compute for being processed. So your most costliest compute element is sitting idle 50% of the time because it's waiting for the data to arrive or go, right? And
Mhm.
hence we are talking about networking being the bottleneck to ensure the higher utilization of the costlier compute element. And to
Mhm.
do that, there are many things that we need to do. Is that how do we accelerate this networking? So there are two ways. One, we have been on what we call as an Ethernet technology or a copper technology, and we have been scaling that up to say is that can we make it faster and faster and faster, and we'll continue to do that. There are methods we have been leveraging to do that. The second one, we figured it out and we said that how can we use lights or optics so that
Mhm.
we can also start moving the data using that medium and then probably make it more faster, maybe less power, and then can it fit into the cost that we have is there. So you will see networking will have a mix of what we call as electrical as well as optical that's coming in and trying to run and drive things about fast, like low latency, high bandwidth, low power, and then all of that. So that's where networking is being moved. And there are a lot of elements that comes in, what is right next to the server, what versus what is in the network, and then there are some in between so-called as elements, and then finally to the another node or another server. There's a large networking pipe that's there and huge amount of invention or innovation that's happening there.
Mhm. So we have spoken about compute, we have spoken about the network, but storage is also something that is often overlooked when it comes to AI conversations. So what architectural changes are necessary according to you to ensure that the storage keeps pace with the compute and the networking?
Yeah, so there are again that's what so I think let's look at storage in two ways, right? There is what we call as during the processing you need a lot of storage because you are like the workload is big, your processing data is big, and while you're processing it is not in one step, you might need multiple steps. So you need access to a local storage, and that's where we talk about saying what's the size of the storage that's available and then how fast that is, right? Versus there are a lot of times when you have to send the data out through the network and through a more so-called as a more reliable and more scalable and a more long-term storage that's come there. So the architecture in two cases is that one, scalable, expandable, and then low latency, fast throughput, versus the second one is reliable, secure, right? And then cost perspective, because it's a large data that we are doing that, right? So those are the two drivers to say is that again, what kind of storage comes in. We have started seeing that each processing unit has the limit about saying how much memory can you put in because our chips are becoming complex and one metrics of seeing complexity is just the size of it. We're just increasing the number of transistors and so-called as features that we fit in. And beyond some time, there's so much less space left for the memory because the processing itself is taken care. That's where we started getting into what we call as a complex 3D kind of a integration of the chips where we have the processing chips and then the IOs and memories are shifted outside and access that. But can we start expanding it to be shared across multiple XPUs and have it at a low latency are the architectures that we are trying to build on.
Mhm. So as systems are becoming more complex and specialized in the past recent years, we must have definitely noticed that different technology and systems are becoming more complex and specialized. So how do you balance performance optimization with flexibility and long-term scalability?
Yeah, so very good observation. We talk about what we call as a performance, cost, and power, but I think you bring it about long term, right? What we see around today, data is changing almost every day, every week. You and I are generators of data, and that becomes the so-called as a training set for like all the models and everything else.
Mhm.
So data is changing at a daily speed. Every week we have a new models coming in from the big companies who are optimizing the model, and then there's a large language model, there's reasoning models, there are small models and other stuff. And then we have every week or month many applications or APIs that's coming in to use AI for what we call as improvement in the uh, efficiency or so-called as new features and all of that, right? But a semiconductor development cycle to be fit into this AI is a 2 to 3 year cycle. I cannot make chips in a year or at that same frequency with which the data models and applications are changing. So what it means is that we have to build the foundation in such a way that 3 years down the line, when my architecture and the silicon is ready, it still fits into the changed or evolved data model and AI applications. So there's a lot of thought process that goes into about saying is like, what would be the architecture and the requirement for this hardware infrastructure so that I can fit in these massive growth that's happening from the other side at a very fast speed. And that's where a lot of innovation comes in. And that's why you see this concept of purpose-built versus a custom silicon, right? Uh, Look at simply from our use case, right? We use AI sometimes probably because we are watching an OTT and we want to know what is the other recommendations. Similarly, on e-commerce side, but then there's a lot of so-called as enterprise use applications, writing codes, building circuits, generating documentation, and all of that. So there are all very different use cases. And then when each company is looking at it, they're figuring out saying, how do I create a purpose built or a custom built silicon? And then the driver was one saying like, what is the use case that I'm trying to solve? But the metrics that we are trying to optimize or outcome that I'm to measure, the the big one is, I would say, is that what we call as power and the total cost of ownership. I
Mhm.
think performance comes as part of it. There's been a long decades of when we used to measure the outcome only by performance. It has become the not the second order of parameter, but not the first order like the way we call power and TCO, because we are calling each silicon to be probably taking 800 watts, 1000 watts, 1500 watts of power and talking about millions of being stacked together. Each of this silicon costs no more in three-digit dollar or four-digit dollar, but going into a five-digit dollar kind of a price for each of this chip. And how do I optimize this along with the cooling that I have to put in, the amount of so-called as a complex heterogeneous integration that I have to pull in and connect this to make it a system that will work for all of us, right? So that's where the architectures are coming more tops down about saying what the top system looks like, what will the software and how will hardware be interoperable with this, and then be relevant for 3 years as well as fit into the cost curve and the power curve that we are measuring against.
Mhm. Definitely. And shifting the gears here a little bit, talking about security. So, security is
Mhm.
becoming a hardware level concern. And how do you approach integrating security into silicon without compromising performance?
Yeah, so security has to be built in and then across layers, primarily because I mean, let's just acknowledge, right? You could have data that could be biased or be what we call as a bad data because of a corruption. You could have models which is built on some thought process and then training sets and then other stuff. So again, it could be corrupted or all of that. And then you have the hardware itself saying how does it handle when you are interacting between millions of them, either in the same floor or a real estate space or across the city, countries, and continents, right? And then hence the security needs to be embedded all around from top to bottom.
Mm,
Specifically, that's what we have seen is that it has to be built bottoms up. Uh, how do we build the basic root of trust and the security module in hardware itself is an important part of it. So that gets built in. Does it has an impact on performance? Maybe at times, yes, but that's what we realize is life more important, security more important versus performance. I think we all know the answer. So we make those calls, but it's not always that it impacts a performance directly. It can impact maybe some part of a cost angle or the development cycle and other things that comes in because you have to fit in a specific IP, you have to build in an architecture, you need to integrate that, you need to test it much further in different use case to validate that. But once we build that hardware, you take it to the firmware and the software that gets loaded. Again, there is what kind of synchronization we are doing it, what kind of, footprint of the software and hence the security layer we put in that comes in. The third comes in is that in the supply chain, because when we are manufacturing this, validating it is crossing different geographies and all. So avoiding counterfeit versus also saying what kind of security threats that could come in because we connect it into different pieces on the board. There are standard interfaces where the data could come in and it could have a so-called as a bad input along with a good data. So again, there is a level of testing and validation and security checks and balance that builds in. And then finally, you go up into the software application layer, which is where the cloud companies come in. They need to build the security as well when the data is moving out and then across the boundary, both physical as well as geographical boundaries. So it's embedded right through. It is part of the cost equation. It is part of the thought process that things could go wrong, and hence, what do we do? right from the basic IP or building block all the way to the system and the software level.
Mhm. So now talking a bit more on, how India is positioning itself in strongly in semiconductor ecosystem. So from a technical and ecosystem standpoint, where do you see the real progress and where would you notice, that certain gaps still remain?
That's an exciting journey, right? What was seen as a ground for competency, right? The first C, because of which the large R&D companies came in, the product companies came in. Slowly, it became the second C, which is consumer, because of our population, because of our aspirations, because of our so-called as ability to use different things. We became the consumer for the world, and hence we came in. And I think the transition is happening to the third C. What we say is that, hey, create for the world, right? We are trying to start innovating from the bottoms up and create not just for India, but for the world, right? That's a transition we are in middle of it. Thankfully, we have a very good program called as the India Semiconductor Mission, where we have support right from the top, from government saying, "Hey, I'll support it both financially as well as policy driven and the business environment." But also an acknowledgement from the ecosystem that this is a time that we reduce the dependency on the import that we do on electronics and try to be an equal player and partner in the global semiconductor ecosystem. I think that's the form India is taking, is to be a partner, to be an equal player, and then be part of the overall supply chain that we build in. The journey has been that we have the first level of what we call as the manufacturing footprint that has started. It was approved. Some of them have started. Some of them are in groundbreaking and other things. And it's moving well so that we are part of that supply chain. What it means is that it's not just manufacturing, it's factory or machines. There's a lot of raw materials and other so-called as things you do before manufacturing and do after manufacturing. So I think those needs to come in as well. So the next focus is on saying, how do we create a complete supply chain? What materials, chemicals, gases, airs, and other instruments, mechanical, logistics, and everything comes together so that the supply chain is complete and we can ensure that this is an efficient supply chain rather than just manufacturing, but then we are moving rest of the world for all other things. So that's moving well. The second part of it is that what we call as a design-led manufacturing, right? You can create the manufacturing, but who will fill those fabs and OSATs houses? So you need to have design ecosystem, product ecosystem. Yeah, that's where the second part of the policies and focus comes in. Good progress, but not enough. We need hundreds of those IP and product startups, which is creating chips for different use cases across the world, whether it's processor, networking, storage, sensors, and many other things. And it could be a mix of many technologies. You don't need the traditional silicon or a CMOS technology. A lot of our use case could be on sustainability, mobility, and many other use cases where you will need specialized foundry along GaN or silicon carbide, right? And products which is power electronics, high voltage devices, and other stuff. So there's progress happening, but needs to be accelerated. And I think that's where we are hearing that the next phase of the mission will have focus to accelerate these IP and product creation by enabling better policies, by enabling bigger fundings, by bringing in more ecosystem players, whether it is the funding houses and a research ecosystem and all of that, and make that successful. That's the second part of it. And third part of it is basically how do we go and sell it, right? You can have manufacturing factory, you can have an IP product, but you don't sell a chip. You finally sell a full assembled product, whether it's a phone, whether it's a charger, whether it's any devices. Who are those system integrators and ODMs and OEMs and the end product companies who make a products and then make it available to the wide audience and across the world, right?
Mhm.
That part I would say is still a work to be done because we are still dependent on global houses to take these chips and integrate and get a product out and sell to us, versus we would want a balance of local houses as well, saying whether it's a home appliances, whether it is industrial automation, whether it is space and defense, whether it is data center or 5G, we will need those end product companies to do that. So I think that one is slow and need focus that's coming up. So that's where the landscape is. It's definitely exciting. It's a positive move forward in our journey? Is it sufficient? No, but are we progressing and have the right priority? Absolutely, yes.
Definitely. So it is quite exciting to see how the next phase of data center architecture evolution will also be happening. Like saying in the next decade is, too long. It could be just 1 year, it could be just 2 years. So it was very interesting to learn all about, what goes behind a data center. So thank you so much, sir, for joining us today and helping us with your industry insights on this matter.
Absolutely. I think I can, I can summarize this saying, right, semiconductor is the foundation. It's now recognized and acknowledged. There is enough focus globally and in India to create the right ecosystem. No one country or one company will solve it. It will be a collaboration across the geographies, across the borders to build that ecosystem in a collaborative way. And then there are building blocks that will drive it bottoms up. Core semiconductor research will drive saying how much more we can accelerate this and bring this so-called as intelligence in our hands, around us, and our ecosystem, so to have a better future. So very exciting time for us, and India will be a key equal player in this in coming years. But be patient. It is not a months or years journey. It will be 5 years and decades journey.
Thank you so much, sir, for joining us. Thank you.